In the summer of 2024, a Chinese spacecraft touched down on a part of the moon no human instrument had ever physically sampled before, the far side, the hemisphere that permanently faces away from Earth, hidden from our view for the entire history of human civilization. That mission, Chang'e 6, scooped up roughly 2,000 grams of lunar soil and rock, then did something nothing had ever done before, launched itself directly off the far side, and carried those samples all the way home. In the 2 years since scientists first got their hands on that material, a series of careful laboratory studies have revealed something genuinely unusual buried inside those rocks. Physical evidence of an ancient collision so violent it tore straight through the moon's outer crust and into its actual mantle, the deep, hidden layer beneath, dragging material up to the surface that has otherwise remained buried for over 4 billion years. And the story does not stop there. That same violent impact appears to have literally boiled away certain chemical elements directly out of the moon's interior, leaving behind an isotopic fingerprint scientists can still measure today. A fingerprint that may finally explain one of the strangest, longest standing mysteries about our own moon, why its near side and far side look so completely different from one another. This is the real story of what scientists have actually found hidden in these unprecedented lunar samples, and why it matters for the astronauts NASA is currently preparing to send back to the moon's surface. Landing on the moon's far side at all represents a genuine engineering achievement in its own right, one worth appreciating before getting into the chemistry itself. Because the far side permanently faces away from Earth, any spacecraft attempting to land there loses the ability to communicate directly with mission control back home, since our own planet is never visible from that hemisphere to relay a signal. China solved this problem by placing a dedicated relay satellite, named Queqiao-2, in a specific orbit positioned specifically to maintain a continuous communication link between the far side lander and ground controllers on Earth throughout the entire mission. Chang'e 6 touched down within the South Pole Aitken Basin on June 1, 2024, drilled into the surface and used a robotic arm to gather material from multiple depths, then launched an ascent vehicle carrying those samples back into lunar orbit, where they were transferred to a return capsule and ultimately delivered safely to Inner Mongolia on June 25, 2024. The entire sequence represented the first time in the history of spaceflight that any nation had successfully returned physical samples from the lunar far side, a genuine first that immediately made this specific batch of roughly 2,000 grams of rock and soil among the most scientifically valuable planetary samples currently available to researchers anywhere in the world. To understand why this discovery genuinely matters, you first need to understand exactly what the South Pole Aitken Basin actually is, and why scientists have wanted to get physical samples from it for decades. Stretching across roughly 1,500 miles of the moon's far side, the South Pole Aitken Basin is the largest confirmed impact structure anywhere on the lunar surface, and one of the largest impact basins known to exist anywhere in the entire solar system. It formed when an object, almost certainly an asteroid, struck the moon with enough force to blast out a crater deep enough to punch through the moon's outer crust entirely, an impact so powerful that scientists have long suspected it must have excavated material from the mantle, the thick, hot layer of rock sitting directly beneath the moon's outer crust, material that, under ordinary circumstances, remains buried far too deep for any surface mission to ever directly access or sample. For years, this remained a genuinely compelling theory rather than a confirmed fact, based mostly on remote sensing data collected from orbit, which had detected spectral signatures suggesting mantle-like material might be present somewhere within the basin, without ever being able to confirm that interpretation with an actual physical sample in a laboratory. Chang'e 6 finally changed that. Landing within the South Pole Aitken Basin itself, at a site named Statio Tianjiang, the mission collected material, specifically from this scientifically critical region, and returned it to Earth, giving researchers their first ever opportunity to directly analyze physical rock samples from this specific, uniquely important part of the moon. What scientists found, once they finally got these samples into laboratories, exceeded even those long-standing expectations. Multiple independent research teams, publishing their findings across late 2025 and throughout 2026, identified rock fragments called norites among the returned samples, a specific type of rock whose mineral composition provided direct, physical confirmation that the material had indeed originated from an impact melt sheet, a layer of rock that had been completely melted by the sheer force and heat of the original impact, then slowly cooled and crystallized over an extended period afterward. Detailed chemical analysis of these norite samples revealed a composition dominated by a mineral called orthopyroxene, consistent with a source deep within the lunar mantle, combined with a smaller contribution, estimated at roughly 20 to 30%, from the moon's outer highland crust that had been swept up and mixed in during the same violent event. Based on this evidence, researchers determined that the impact had triggered a genuine reorganization of the moon's crust and mantle in this specific region, forming a distinct three-layer structure, with dense, mantle-derived dunite at the very bottom, a thin intermediate layer of orthopyroxenite and norite, the specific rock type actually collected by Chang'e 6, forming the uppermost portion of this entire ancient, deeply buried structure. Precise radiometric dating of these same samples, using the decay of lead isotopes within tiny zirconium-bearing mineral grains, allowed researchers to establish an unusually specific age for this ancient, transformative event 4.25 billion years, anchoring one of the oldest and most significant impacts in the Moon's entire geological history to a remarkably precise point in time, providing scientists with a valuable new reference point for calibrating the broader timeline of bombardment across the early solar system. This specific dating technique works by measuring how much uranium within these tiny mineral grains has gradually decayed into lead over time, a process that occurs at an extremely steady, well-understood rate, allowing scientists to calculate backward from the current ratio of these elements to determine almost exactly how long ago the mineral grains themselves first crystallized out of the molten impact melt. Researchers actually identified two distinct ages within the analyzed samples. A younger age of roughly 3.87 billion years, which they interpreted as a later, separate impact event that reset the chemical clock within a portion of the material, and the older, 4.25 billion year age, which the research team concluded most accurately represents the original South Pole Aitken impact itself. This specific figure matters enormously for planetary science well beyond the Moon alone, since scientists studying impact craters throughout the solar system frequently use the Moon's own well-documented cratering history as a kind of calibration standard, extrapolating from precisely dated lunar impacts to help estimate the ages of similar craters found on other worlds, including Mars and Mercury, where no comparable sample return mission has ever been possible. This alone would represent a genuinely significant scientific achievement, confirming a decades-old theory about one of the Moon's most important geological features using real physical evidence for the first time. But a separate line of research, examining these same general samples from an entirely different angle, revealed something considerably stranger. Evidence that this ancient impact did not simply excavate and rearrange existing lunar material, but actually altered its fundamental chemical composition through direct physical force. A research team analyzing basalt samples returned by Chang'e 6 conducted high-precision measurements of two specific elements, iron and potassium, comparing the exact isotopic signatures found in these far-side samples against equivalent measurements taken from both the Apollo program's near-side samples and China's earlier Chang'e 5 mission, which had also returned material from the Moon's near side. The results showed something genuinely unexpected. The Chang'e 6 far-side samples consistently showed measurably heavier iron and potassium isotopes than either of the near-side sample sets. A difference the research team determined could not be adequately explained simply by ordinary volcanic or magmatic processes or by contamination from the original impacting asteroid itself. For potassium specifically, the researchers concluded that the most likely explanation involved a process called evaporation, meaning the sheer heat and force generated by the South Pole Aitken impact was intense enough to physically vaporize a portion of the potassium originally present in the local mantle material, with the lighter isotopes of that element preferentially escaping as vapor, while the heavier isotopes remained behind in the surrounding rock at a higher relative concentration than would otherwise be expected. In effect, the ancient impact did not just crack open the Moon and expose its interior. It appears to have partially cooked away specific chemical elements directly out of the mantle material it excavated, leaving behind an isotopic signature detectable in laboratory instruments more than 4 billion years later. This finding carries genuine significance far beyond simply being an interesting chemical curiosity. It provides direct physical evidence supporting a broader hypothesis scientists have proposed to explain one of the most persistent puzzles about our Moon, the striking, unmistakable difference between its near side and its far side. Anyone who has ever looked up at the Moon has seen its near side, covered in the dark, smooth patches of ancient volcanic rock that give the man in the Moon its familiar face. The far side, by contrast, is covered almost entirely in pale, heavily cratered highland terrain, with dramatically less evidence of the same kind of extensive volcanic activity, a difference so pronounced that scientists have debated its underlying cause for decades. This asymmetry has puzzled lunar scientists since the earliest spacecraft images of the far side were first captured by the Soviet Luna 3 probe back in 1959, and it extends well beyond simple visual appearance. The Moon's crust is measurably thicker on the far side than on the near side, sometimes by tens of kilometers, and the near side additionally contains a concentrated region of specific heat producing radioactive elements, popularly referred to by the acronym CREEP for potassium, rare earth elements, and phosphorus, a concentration almost entirely absent from the far side's own crust. Various competing theories have been proposed over the decades to explain this fundamental asymmetry. including the idea that Earth's own heat, radiating outward during the moon's earliest molten history, may have kept the near side warmer for longer, slowing its cooling and crystallization relative to the far side, or alternatively, that a separate, smaller companion moon may have once orbited alongside our current moon before eventually colliding with it, its remnants merging into what we now recognize simply as the far side's unusually thick crust. The new isotopic evidence from Chang'e 6, combined with the confirmed scale and violence of the South Pole Aitken impact itself, supports a related but distinct idea that this single ancient collision may be directly responsible for at least part of this long-standing near-side, far-side asymmetry, having fundamentally altered the composition, structure, and subsequent volcanic history of the mantle material, specifically underlying the far side, in ways that never affected the near side at all. Rather than requiring an entirely separate, exotic explanation, such as a second merged moon, this evidence suggests at least part of the answer may simply be sitting within the chemistry of the South Pole Aitken Basin itself, evidence that had remained completely inaccessible until Chang'e 6 finally brought physical samples home for direct laboratory analysis. A separate complementary study examining lead isotopes within different Chang'e 6 impact melt fragments reinforced this broader picture even further, concluding that the crust in this specific region of the moon is not simply a straightforward primary product of the moon's original formation, when its entire surface is believed to have been covered by a global ocean of molten rock, called the Lunar Magma Ocean, that gradually cooled and solidified over time. Instead, the research indicated that the crust in the South Pole Aitken region had been genuinely reworked, melted, and differentiated a second time, well after that original global magma ocean had already finished solidifying, driven specifically by the heat and force of this single colossal impact event. Researchers involved in this work have described the resulting picture in strikingly direct terms, characterizing it as evidence that the moon's geological history has been far more dynamic than previously believed, with giant impacts capable of acting as powerful agents of genuine planetary transformation, reshaping a world's fundamental composition long after its initial formation was supposedly already complete. Here is where this entire body of research connects directly to what NASA is actively planning right now, in 2026. A team of scientists working with the Center for Lunar Origin and Evolution, a NASA-affiliated research organization led by the Southwest Research Institute, has been specifically studying how this same colossal impact likely scattered mantle-derived material across the surrounding lunar surface. Work directly relevant to the Artemis program's own planned landing sites near the lunar South Pole. By modeling the specific physics of a low-angle strike from a large iron-cored impactor, the kind of object researchers believe actually created the South Pole Aitken Basin, this research team determined that considerable amounts of genuine mantle material were likely blasted outward from the impact site, and now sit scattered across a wide surrounding region, some of it potentially close enough to areas NASA is already targeting for future crewed Artemis missions that astronauts could conceivably walk across it directly, without needing to drill or dig anywhere near as deep as the mantle's actual depth would otherwise require. This modeling work specifically accounted for the angle and direction of the original impact, since a low angle, glancing strike rather than a straight vertical collision, tends to excavate and scatter material asymmetrically, throwing debris preferentially in one particular direction rather than spreading it evenly in every direction around the impact site. By reconstructing this specific geometry, researchers were able to identify particular regions surrounding the South Pole Aitken Basin where mantle-derived ejecta is most likely to be concentrated at or near the surface, effectively producing a targeted map of where future explorers would have the best realistic chance of encountering genuine mantle material without extensive excavation. Given that NASA's Artemis program has specifically selected candidate landing sites clustered near the lunar South Pole, partly because of the water ice believed to be preserved in permanently shadowed craters in that same general region. This new mapping work raises the genuinely exciting possibility that a single Artemis mission could eventually study both of these scientifically significant resources, ancient mantle material and preserved water ice, within a comparatively limited exploration radius without requiring entirely separate missions to entirely different parts of the moon. This is a genuinely remarkable practical implication. Ordinarily, directly sampling a planetary body's mantle requires drilling or excavating to depths far beyond what any current human or robotic technology can realistically achieve. The South Pole Aitken impact effectively did that excavation work already, 4.25 billion years ago, scattering genuine, deep interior material across the surface in a way that considerably simplifies the practical challenge of studying it today. If future Artemis astronauts land within reach of these specific deposits, they could potentially collect and return samples of authentic lunar mantle material using nothing more sophisticated than the same basic collection tools already used throughout the Apollo program, rather than requiring any specialized deep drilling equipment that does not currently exist. It is worth being precise and honest about exactly how settled all of this research currently is, since that precision is exactly what separates genuine scientific progress from overstated certainty. The specific 3-layer model describing the basin's internal structure, the precise 4.25 billion year age determination, and the proposed connection between this single impact and the moon's broader near side, far side asymmetry, all represent serious, carefully conducted peer-reviewed research, but they also represent an active, ongoing scientific investigation, rather than a single, final, universally agreed upon conclusion. Different research teams analyzing different specific samples and isotopic systems have proposed complementary, broadly consistent but not entirely identical models for exactly how this ancient impact reshaped the moon's interior, and continued analysis of the remaining Chang'e 6 samples, alongside comparison with samples eventually returned by future missions, will likely continue refining and testing these specific conclusions for years to come. Step back and consider what this entire body of research genuinely represents about the value of returning physical samples from previously unexplored places, rather than relying purely on remote observation from orbit. Scientists had suspected for decades that the South Pole Aitken Basin likely contained excavated mantle material, based on spectral data collected from a comfortable distance. It took an actual spacecraft landing directly within that basin, collecting real physical samples and carrying them all the way back to laboratories on Earth, to finally confirm that suspicion directly, and in the process, to reveal something nobody had specifically predicted in advance. Direct evidence that the impact itself had chemically altered the material it excavated, boiling away specific isotopes in a way only detectable through extraordinarily precise laboratory analysis. Remote sensing from orbit told scientists roughly where to look and what to expect. Only a genuine sample return mission could actually confirm what was really there, and reveal the considerably stranger details that orbital instruments alone could never have detected on their own. So here is the honest, complete picture behind what scientists have genuinely found hidden in this unprecedented lunar material. Chang'e 6 returned the first ever physical samples from the moon's far side, collected specifically from within the largest and oldest confirmed impact basin anywhere on the lunar surface. Laboratory analysis of those samples has now confirmed that the ancient impact responsible for that basin was violent enough to excavate genuine material from deep within the moon's mantle, chemically altering that material through the sheer heat and force of the collision itself, and potentially explaining for the first time with real physical evidence why the moon's near side and far side look so strikingly different from one another after more than 4 billion years. And the same ancient collision may have conveniently scattered authentic mantle material, close enough to NASA's planned Artemis landing sites that future astronauts could potentially study genuine lunar interior rock simply by walking over and picking it up, without ever needing to dig anywhere near the depths that material actually originated from. If you want to see what future Artemis astronauts actually find when they eventually search these specific deposits for themselves, subscribe and turn on notifications, because scientists have already said this ancient impact still has more secrets buried in it, and the next chapter of this story may be written directly on the lunar surface itself.